So we'll be discussing a problem, repeat and missing number array, where you're given an array, read-only array of n integers, which contains which are from 1 to n. Each integer appears exactly once except a, which appears twice, and b, which is missing. So we need to return a and b. So the algorithm must have a linear runtime complexity. Also, it must not use any extra memory. So also the order of the output also matters. We must return a followed by b. So let's see the sample input. So here's the given array of size 5. So that means this must contains all the elements from 1 to 5. So but we can observe that this does not contains the element 4. So 4 is the missing element here. We can also observe that the 3 is appearing twice here. So 3 is the repeating element. So the answer will be the repeating element followed by the missing element, which is indeed here. So 3 followed by 4. So let's think of a brute force solution first. So here's the array. Now how we can solve this problem? Basically, we can think in the naive solution for this problem can be simply to sort the array. So if we sort the array, then what will happen is that the duplicate elements will appear adjacent to each other. So if they appear adjacent to each other, it will be very easy in a single traversal. So after sorting, we traverse the array and we compare the adjacent elements, and if the adjacent elements are equal, then that element is the repeating element, and we put it into a set. Now to find the missing element, we simply compare the given array with the ideal array. The ideal array is the one which contains all the element from 1 to n. So for that, we simply initialize the counter C with 1 and start traversing the array from the first position and compare the element at each position with the counter, and increment the counter as we move the pointer. So initially the counter is 1 and the value here is also the same. Now we increment the counter because we need to find the next value, which is 2. So we move the pointer here. 2 is not here, so we move the pointer here. Yes, we find the 2 here. So now we increment the counter to 3. So now it is 3. Now we need to find the value 3. So we move the pointer to the next. We found 3. So we have found 3. Now we increment the counter to 4. Now we iterate to the next element, which is 5. That means this element is greater than 4. So we have not found 4. So that's why 4 is the missing element. So we put 4 here. So this is the answer set. So what is the time complexity of this solution? We're simply sorting the array, which will take big O of n log n. And then we are iterating over the array that will take big O of n. So also we are iterating again for finding the missing element, so that will also take big O of n. So the overall time complexity is big O of n log n. Now what's the space complexity? Since we are not using any extra space, the space complexity is constant, big O of 1. So let's see the algorithmic steps. Now the solution here simply modifies the array. So it rearranges the array element in the sorted order. But in the given question, the array given is a read-only array, means it cannot be modified. Also, the time complexity of this solution is not linear, but we want linear runtime solution. So we need to optimize this solution. So how we can optimize it? Well, let's think about it. We need to find the element which appears twice in this array, and an element which does not appear at all, and the range is 1 to n. So that means we can simply keep the count of each element in some container, and if the count of some element is 2, that means that element is the repeating element, and if the count of some element is 0, that means that element is missing element. So this approach is called hashing, where you simply declare a frequency array and initialize it with 0. Now we start iterating the array A, and we increment the frequency of each element we are traversing. So initially we are traversing 1, so we increment the frequency of 1 by 1. Now we go to the next element, it is 2, so we increment the frequency of 2 by 1. Now we go to the next element, we increment the frequency of 1 by 1, so it is 2 now. Now we go to the next element, it is 5, we increment the frequency of 5 by 1. Now we go to the next element, we increment the frequency of 3 by 1. So now we have traversed the whole array and counted the frequency of each element in the frequency array. Now we can traverse the frequency array from 1 up until n and check if the frequency of some element is 2, that means that element is repeating element. So the frequency of 1 is 2, so 1 is repeating element. Then we iterate and find if the frequency of an element is 0, means that element has not been seen in this array, so this is the missing element. So 4 is the missing element, so we return this set. So this is the hashing approach. Let's discuss about the time complexity. Since we are iterating the array for building this frequency array, so this will take a big of n. In the second iteration, we are iterating the frequency array, which will also take big of n. So the overall time complexity of this solution is big of n. Let's talk about the space complexity of this solution. Since we are using a frequency array of size n plus 1, the space complexity of this solution is big of n. So as compared to the previous solution, this solution does not modify the input array, but it uses extra space. So the runtime complexity of the solution is better, but the space complexity of this solution is worst. So but the requirement of the problem says that we have to do it without using extra memory. So there is a even more optimal approach which exists. So let's think about it. The next approach that we're gonna discuss here is based on the properties of XOR. So this approach is not very intuitive, but once we learn this, it will be very it can be solved, it can be used in many problems. So let's discuss about it. So what is XOR? Bitwise XOR operations are such that if we perform bitwise XOR between the non-matching binary bits, namely 1 and 0, then we always get 1. So the XOR of 0 and 1 is always 1, while the XOR between the similar bits gives us 0. That means if we perform bitwise XOR between the similar elements, that will always give us 0. Hence for getting to the real solution, first we discuss this problem. We're given an array such that all the elements appears twice in this, while one element appears unique. So the task is to find that element, that unique element. So since we know the XOR properties, we simply XOR all the elements of the array and those elements which appears twice will cancel each other. 2 will cancel 2, 1 will cancel 1, 6 will cancel 6, and we are remaining with the unique number which is 5. Since this array contained duplicates, we used this XOR. So now let's go to the we will be building our solution based on this property. So let's go to the original question. So here is the given array. In this array, every element appears uniquely except one element which appears twice. So we need to create that duplicacy here. So what we do is we simply XOR all the elements of this array and we XOR the elements of the ideal array. The ideal array contains all the elements from 1 to n. And we XOR both of them with each other. Now this 1 will cancel this, 2 will cancel 2, 3 will cancel 3, 5 will cancel 5. So we are remaining with 1 and 4, because this 4 is not present in the original array, while this 1 is present twice in the original array. In both the cases, 4 and 1 will remain as it is. So 1 will be cancelled by 1. There is only one single 1 remaining and the single 4 remaining. So we can see that 1 is the repeating element and 4 is the missing element. So the resultant of this XOR will give us the XOR of repeating element with the missing element. This is 5. So I have written the same operation here, where the first 5 elements represents the elements of the array, while the last 5 elements represents the elements from 1 to n. So the resultant is 5. Now this resultant is same as the bitwise XOR of repeating and missing element that we can observe here. Now what is the key observation here? And the key observation is that for this bit to be set, namely the first set bit from the right side to be set, one of the bits from the duplicate element or from the repeating element must be set. So that is the key observation. That means one of the bit in the repeating element or in the missing element must be set, and other bit and the same bit in the other element must be unset. Only in that case we can obtain 1 here. Okay, so the task is to segregate them. So this property can be used, like what we can do is we can segregate this whole set into 2 sets, where the first set contains all those elements which contains 0 at this position. So that contains 2, it contains 2, this 2 and this 4, and we perform bitwise XOR between these. So 2 XOR 2 XOR 4, 2 will be cancelled by 2 and we are remaining 4. So X represents that set. Now we perform bitwise XOR among the elements of another set which contains all those elements which has this bit as set. So namely 1 1 5 3 1 3 5. So 1 will be cancelled by 1, 5 will cancel 5, 3 will cancel 3, and we are remaining with 1 here. So y is 1. That means these 2 sets, the idea was that the either two like these two sets, one of them must contains exactly one of the repeating or missing element, and other must also contains one of the repeating or missing element. Single set cannot contain both of them because of this property. Okay, so now we have segregated the missing element and the repeating element. The next task is to find which one is missing and which one is repeating. For that, we can traverse the array from left to right and check if x appears there, that means x is the repeating element and y is the missing element, and otherwise if y appears in the array, that means y is the repeating element and x is the missing element. So we return the output set. Now let's discuss the time complexity of this solution. So since we are traversing the given array once, that will give us a linear time complexity, plus we are iterating from all the elements from 1 to n, that will give us another linear factor, plus we are also segregating the two sets, that will give us another big O of n. So the overall time complexity is big O of 3n, which is same as big O of n. So this solution, so let's discuss about the space complexity. So in this approach we haven't used any extra space, we simply use the XOR property and we perform the task. So the space complexity is constant, it's big O of 1, so it is using constant space. So this solution is better than the previous solution which was using a linear space. So does this satisfy all the requirements of the problem? Yes, it has a linear runtime as well as it does not use any extra memory. So let's see the steps of this approach. Okay, so let's go to the implementation part. So here is the function repeat number, which takes in a vector a, and this vector represents the answer. It will return the repeated number and the missing number. N is the size of the array, x is the first set, y is the second set. XOR contains the bitwise XOR of all elements of the array and the elements from 1 to n, and this mask basically is used to segregate the first set bit from the right side. So this mask contains all the bits unset except the first set bit from the right in this XOR. Now we iterate over the array and check all the element which contains this bit as set. We put them into the set x, and all those elements which does not have this bit as set, we put them into y. Now we have x and y. We want to find which one is missing and which one is repeating. So we iterate over the array. If we find x in the array, that means x is the repeating element and y is the missing element. Otherwise we find that y is the repeating element and x is the missing element. So we push the repeating element first, followed by the missing element, and then we return the answer. So let's so that's the okay. So thank you very much.